All right, how's it going, everybody? We are here on Friday, February 19th. Today we're going to talk about section 1.4, which is going to be very closely related to 2.4, or I believe if you're in the fourth edition, 2.5, which is covering Euler's method, a numerical approximation technique for approximating the solutions to differential equations numerically. This technique is going to directly apply both to individual ordinary differential equations, like our stuff in chapter 1, as well as to systems. We're essentially just going to need to do double the work for the systems because we have two variables to follow, but everything is going to kind of work the same. The good thing about this technique is that this works for any ordinary differential equation. As long as you are able to plug in numbers into your dy dt and dx dt equations and get out numbers for dy dt and dx dt, then this technique is going to work right here. So this has nothing to do with our ability to solve a differential equation whatsoever. No dependence whatsoever on integration, only dependence on a large amount of calculation. That leads us to the major con that's associated with this, which is that it's always going to be just an approximation. This technique was really discovered hundreds of years ago. I mean, it's called Euler's method for a reason, because it's named after Leonhard Euler, who was like, mid 1600s. He's the guy that kind of first formalized this technique right here. So this was come up with hundreds of years ago, but this technique has really never been practically useful for us until the advent of computers, basically. To get good approximations, the better we want our approximation to be, the more calculation that we need to do. And so coming up with good approximations takes huge amounts of calculation, which we don't ever want to do by hand. So this is really sort of one of those things where, like, just because we knew how to do this doesn't mean it was practical to do it up until we had computers to finally be able to help us out with these things here. So that is to say, thank goodness we're here, and thank goodness that, and not only like was this not practical until like the 70s with computers, but even then you would probably have to take like an entire class on learning how to write a program to be able to do this, whereas we are going to learn to write a program in just like 1 hour right here, having I'm expecting no programming experience from you whatsoever for us to be able to do this today. You guys are going to kind of follow along with what I'm doing, and what I'm going to hope to ask you at the end of the day is for you to update the code that we've written to handle a system rather than an ODE on your own, which is going to be probably hard for those of you that have no programming experience, but certainly within the realm of capability for you. I don't think this is an unreasonable thing for me to ask you to attempt to do here. So this technique of approximating things is going to follow the same trend of approximations for like everything in calculus. Rather than determining a smooth, continuous solution to an ordinary differential equation, we are going to sort of walk out the solution in a step-by-step, discrete fashion. In my mind, when I'm picturing what we're doing here with Euler's method, I'm picturing a very similar idea to what we do with Riemann sums with integration. With a Riemann sum, we are approximating the area underneath a continuous curve where the height of the curve is changing. With every infinitesimally small change in x, there is a change in y. But when we make the Riemann sum, we need to travel an entire delta x distance before we experience a discrete jump in the height of the function y. The Riemann sum is our good approximation, or I shouldn't say good approximation, it is an approximation, and what you know is that the smaller and smaller and smaller your delta x gets with a Riemann sum, the width of one rectangle, or another way to say it is the more number of rectangles you have over the same interval, the larger the number of rectangles gets, the closer your approximation gets to the true solution, the actual area underneath the curve, the value of the definite integral. That concept is exactly the same here. We're going to imitate a continuous curve with a chunky group of straight lines, effectively, right? Where things are going to change all of a sudden, just like with the heights of our Riemann rectangles that are out there. And just like with our Riemann rectangles, the more rectangles we had, the narrower they got, the better our approximation got. Exactly the same here. The more times we update our direction of motion, the smaller the width of each time interval, the better our approximation is going to do, and we're going to be able to make some very nice visual representations of those ideas here today. So ultimately, our kind of like one sentence statement here is we're approximating a curve with a lot of small pieces of straight lines. That's all that's happening right here. That's like the essence of what happens in calculus, right? The good news for us is that this algorithm is really freaking simple. It literally is just a slightly more complicated version of y equals mx plus b is all that's happening. So here's Euler's method right here. And I've even written out like more than is sort of necessary. The book gives it an even more concise formatting right here. I'm just putting some more words in here. So, given an initial value problem. So, one thing to note right away here is that we have to be given initial conditions. We're not going to come up with general solutions because what we're not coming up with is anything analytic or algebraic at all. What we're only doing is numerical approximation, so there has to be numbers from which we start to compute on from, right? So, given some single differential equation, as of right now, we're going to do systems also, and an initial condition, so this says that our initial time we have an initial value of y, right? So time 0 and y at time 0. And we need to know an interval over which we're forming the approximation, right? So this is going to be saying from time 0 to time 8 or something like that. And again, this is all the same stuff that you see with Riemann sums. Riemann sums should be your like basis of reference for all this right here, right? So when we did Riemann sums, we're doing things like approximate the integral from 1 to 5 underneath x squared with a delta x of 1/4. All that same information is in this right here, right? So we have our interval of approximation. Very typical that our time, that at the a value right there is going to be 0, starting at time 0 and going up to some time in the future at which we want to know the value of y, b, that's our final time, and some step size, delta t, or a number of steps. Either of those pieces of information is sort of interchangeable. I should either be able to say to you, use a delta t of 0.5, or I should be able to say to you, use an approximation with 8 steps. And either one of those is kind of giving us equivalent types of information right there. So what are we going to do? Well, we're going to obey our differential equation as to how to move. What you should be picturing for yourself right now is a slope field that we've seen. And in fact, maybe I should just bring up a slope field, the most generic slope field for us to visualize here with the system. So I'm going to kind of pop over here real quick. What we're going to do is we're going to say, okay, we've got some initial location. Imagine it's where my cursor is pointing right now at the tip or at the base of this arrow that's floating out of space. Suppose this is our initial condition that we are given. Rather than following a continuously updating thing, I guess the thing to remember here is that although there's a finite number of arrows out here in this field, that's really just because they pre-selected a grid, and in fact, we could even increase the number that there are, right? You could just do this right here, and there's more and more and more and more and more fine segmentation of where the arrows are located, right? What you should be imagining is that really what's happening is there's actually an infinite number of arrows out here. We're just giving a selection of them to help this be visible. If we had an infinite number of arrows, we couldn't read it, right? So come back over here. Suppose we start at like the base of this arrow. Rather than moving an infinitely short distance in the direction that the arrow suggests and then updating, computing our new directional arrow based on our dy and dt, because right now we're looking at a system instead of an ODE, but that's okay. We're instead going to say, well, yeah, let's travel in a straight line in the direction of this arrow for some amount of time. Once we get to a new location, we will then say, okay, now what does our vector say to do from here? Now what direction should we travel? And you should notice that this arrow is a bit steeper. So now maybe I'm going to travel for some length of time in exactly that straight line distance as indicated by that vector. Once we arrive at the new location for whatever that delta t amount of time that we traveled is, we will then stop and say, all right, let's now recalculate what our dy dt should be at this location. Oh, it looks like we're even a little bit steeper. Let's now travel in exactly the direction of just that linear vector right there for some delta t unit of time. So what we're doing is we're doing these discrete time steps where we say travel in a straight line for a little bit, now update our direction. Now travel in a straight line for a little bit, now update our direction. Now travel in a straight line for a little bit, now update our direction. So we're doing these updates only every delta t units of time rather than every infinitesimally small unit of time. That's the difference between our continuous and our discrete here. Right? So back to our words over here then. We want to start at our initial y value. We have to know a place that we're starting from so that we can compute the rate of change of y. Right? And again, we're back to a single ODE right now. Right? So we're given a starting number of y. And you should notice that by plugging in the time and the y value that we currently have, we can determine how y is changing at that time and at that place. We can then use this differential equation f of ty to compute the rate of change. And think slope here because we're literally doing linear motion always. This is just lots of straight lines that are being tacked onto each other right here. We want to find the rate of change of y when y is at that initial y value and when t is at the initial time value for step 1. Then let's update y by moving in that rate of change direction for that amount of time. So all we're going to do is we're going to say, well, if y0 is where we started, what we want to do is we want to move in the direction of the slope that we've computed. This is really dy dt. And we want to do that for delta t units of time. That will get us to our new y location. Once we're at the new y location, we can again recompute the new slope that we're experiencing, the new dy dt at that time and at that location. And we can use that to inform our next slope. Notice here that delta t never changes. That's constant for the entire time. We're going to pick one constant, delta t. And notice that y sub 0 is just your previous y value. So the only computation we ever have to do is we just need to keep on recomputing what's dy dt at the new location over and over again, and literally just do a y equals mx plus b update. B is your initial value in y equals mx plus b. That's your old y value. The output y is our new y value, the new value of interest for our approximation. And then we just want to repeat this process for whatever the duration of time is, or for the desired number of steps, depending on how we were given that information. So this is literally just saying, do a whole crap load of y equals mx plus b updates, where the old y value is b, and the new y value is y in our y equals mx plus b equation. This literally is nothing more than y equals mx plus b. It's just y equals mx plus b so many times that no reasonable human would come up with a good approximation by hand. It would just be too much by hand work. So, what do we want to do? Well, of course, we want to do one by hand, because it wouldn't be, this is how we really like own this information, right? This is how we like really learn what's happening right here is we're going to do one by hand. Then we're going to verify that our program is going to give us the same results computationally, like with a program, as we got by hand. Then we're going to say it's going to be super easy for us to then say, oh, rather than doing a 4-step approximation, so easy, we're just going to do 4 layers of this by hand, it's going to be nothing to us to increase this number to like 4 million if we want to get the finest approximation that we could possibly get. Trivially easy to upgrade that with the program that we'll write here today. So let's do one by hand here. So what we're going to do is we're going to attempt to approximate a numerical solution. We want to know if y at time 0, if y is 1 at time 0, what I want to know is what value should I expect y to be at time 1. 1 second later, we might think to ourselves. And so I think a good thing for you to do is, like, I don't know, this technically doesn't fit our like harmonic oscillator format right here, but whatever. Picture y being like a position of a mass on a spring or something like that. We are given that at time 0, the mass is 1 unit to the right of where it was initialized, and we want to know where will the mass on the spring be located 1 second later. That's kind of my like potential analogy to this guy right here. All right, so let's go ahead and use Newton's method. Let's do this one by hand. Once we've come up with the Newton's method approximation, let's compare it to the exact answer. You should notice that this is a linear differential equation, and therefore we're actually capable of exactly solving this one. But the point is, remember, we like Newton's method because it can come up with ones that we couldn't do by hand. We're going to do one we can do by hand just so that we can give ourselves that comparison, so that we can say, how good was our approximation relative to the known true correct answer, so that we can trust that this will work for the ones where we don't have anything to compare it to, right? So for this one, we'll also get our exact answer for this guy so that we can compare our approximation to our exact. Then when we go to write our program, we'll improve our approximation and watch it approach our exact answer right there. All right? So step 3 will be write the Python code necessary to perform the approximation. Increase the number of steps from 4 to a large enough number, however big that's going to need to be, to increase the accuracy of the approximation. One of the things we're going to want to discuss over the next couple weeks of looking at these guys here is which techniques converge on the solution at what rates, right? Like, well, I mean, what do you think we're going to need to get to 1 decimal of accuracy of our approximation? It's within 1.1 of the correct answer. Are we going to need to go to 4, 40, 400, 4,000, 40,000, 400,000? The other thing that's going to change is we're also going to look at a different technique next week. Probably our second video next week, we'll look at the Runge-Kutta-4 method, and what we're going to see is it's just a way better method. Rather than doing a linear update to our locations, it's going to do a quadratic update. So because it's going to be a second order polynomial instead of a first, it will have a little bit more accuracy for each of our update steps. So each update step will technically take a little bit more work, but we're going to need way fewer steps of the process to get just as good of answers or better answers out there. So that one will converge on the true solution with much less overall computation because it's a slightly more complicated approximation But the complicated part's not going to be that complicated, really, still. It's going to be still pretty easy to make that guy happen. So let's go ahead and do it here. So we want to do this guy by hand here. And so what we're doing is we're starting with our y of 0 equals 1. What I know that I'm going to need, based on my Euler's formula technique up here, is to compute y1, I'm going to need y0, which we're given. I'm going to need to compute my slope when y is 0, which we can easily do with the differential equation we were given. And notice that I'm going to need delta t. So it seems like one thing we should stop and do first is find out what's delta t in this situation. Notice here that we have been given information that says things like our time interval here of interest is apparently, and I'm going to reference this as a to b. I know that you've seen things that look like this with Riemann sums. We're going to write our programming stuff to look like this as well right here. It seems like our time interval of interest here says start at time 0, pretty common place to start. Our goal is to approximate y at time 1. So it looks like our time interval of interest is 0 to 1, so I would say that's my a value and that's my b value. What I want to know is what is delta t? Well, if we're going to do 4 steps to approximate this, then we have that n is 4. We want to do 4 steps, and so we can find our delta t always by doing b minus a over the number of desired steps. For us, this will be 1 minus 0 over 4. And hopefully you are not terribly surprised whatsoever to see that that means that we're doing a 0.25 as the duration of time that will travel in each linear direction rather than a curvy direction, even though we're expecting curvy solutions out here, right? So we've got our delta t. This says 0.25, 0.25, 0.25, 0.25. That'll give us 4 steps from 0. That should get us to totally time 1 at the end, and we can estimate the value of y once we've reached that, right? So we're starting here at y, and I'll subscript this, y sub 0 equals 1. That's what was given to us right here, y sub 0 equals 1. What I now want to do is I want to use Newton's method to update this guy. So what's y sub 1 going to be? Well, what this is going to say is that somewhere out here in space, we're sitting here at y sub 0. And according to our vector field that we're sitting in, there should be some vector that says you're traveling in this direction. I only want to travel in that linear direction for 0.25 seconds, at which point I will then stop and look at the vector field again and say, well, now what direction do I go in? So rather than a continuously updating direction, it's a discretely updating direction. Do that motion, then do some other motion, then do some other motion, where all those motions are really linear pieces. But what you guys know is if we take lots of small chunks of straight lines, if those chunks get smaller and smaller and smaller and you're sticking them all together, that's gonna end up looking like the curve that we know to expect from this guy, right? So for y sub 1, this should be our y sub 0. By the way, I'm gonna scroll back up here. How do we get our new y value? Well, start at your old y value, go in the direction of motion, the slope, for delta t units of time. So I'm going to start at my old value. I'm going to go in the direction. It looks like we need to do a little bit of side calculation here maybe, or actually, honestly, this one's easy enough. What is my rate of change right here? Well, it's 2 times whatever our y value is plus 1. So my slope here is 2 times whatever our y value is plus 1. That's my slope. And then I want to do that for delta t units of time. That's my 0.25 right here. What I should certainly do right here is say this is y sub 0 plus our dy dt evaluated at y sub 0 times delta t. We're going to go in this direction for delta t units of time. So this is going to give me my y at, so I'm going to also make one little column over here. That's time 0. This should be time 0.25. So 0.25 seconds in, where are we going to be at? Well, it looks like I need to go to my calculator for this guy maybe. I guess I don't need to for this one. 2 plus 1 is 3. 3 times 0.25 is 0.75. So it looks like I'm getting a 1.75 here. So this says after 1/4 of a second, I should approximately be at a y value of 1.75 according to our differential equation. Let's just do a couple more layers of this. Now to get y2, which is 2 delta t's along the way, so we're at 0.5 now for our time, y2 should be based on y1's information. So now I'm going to say we're currently at the location 1.75. Where I want to move from there is the slope at 1.75. So this should be 2 times 1.75 plus 1. and I want to do that for 0.25 seconds. And where am I going to end up? Well, I think I need to go to a calculator at this point here. So I'm going to do 2 times 1.75 plus 1, that's 4.5, times 0.25 to get 1.125. And I add that to my original value of 1.75, my y1 value, to get 2.875. So this is my approximation of where we're at 1/2 of a second into the motion of this system right here, given that at time 0 our y value is at 1. And again, I think I'm going to give myself some labels here. y1, this is now my dy dt evaluated at y1. And this is again my delta t right there. So every time we're just using the old information to get the new information here. So this has to be done step by step. Notice we can't just jump to the next answer. We would have to do a bunch of like function composition. If we were going to do that, it's going to get pretty gnarly. So let's knock out a couple more of these here. We just have to go 2 more steps. Now another 1/4 of a second later at y3, our initial location is the y2's piece of information, right? So this is our 2.875 plus 2 times 2.875 plus 1, right? This is the slope of the solution at 2.875 is exactly this. Our approximating part is that we're going to do it for not an infinitesimally small unit of time, not a dt unit of time, but a delta t unit of time, 0.25 seconds, which in a sense is a small amount of time. So let's update again. I'm going to multiply 2.875 by 2. I'm going to add 1. I'm going to multiply by 0.25. That's giving me a 1.6875, and we're adding that on to our previous value. Plus 2.875. 4.5625. All right, and we've got 1 step left to go. Now we're arriving here at time 1, which is exactly where we wanted our final approximation. To get our y4, we're using our y3 information, right? So 4.5625 plus 2 times 4.5625 plus 1. And we're going to do that for 0.25 seconds. And if I go to my calculator, multiply by 2, add 1. I'm going to do that for a 1/4 of a second. I'm going to get 2.53125. And we're going to add that on to our previous result. So what am I getting for my final approximation here at time 1, y of 1, is adding this to 4.5625, and I'm getting 7.09375. So this is my final approximation for y1. Now, I hope that you, 1, found this to be relatively easy, although it's obnoxious because it's just a bunch of by hand computation. But 2, I hope that you have enough sense to think back to your Riemann sums and you say to yourself, how good of an estimate do you think every Riemann sum was of its respective integral when you only used 4 rectangles? And I'm hoping that you remember that those are pretty bad estimates right there. So I don't think that's going to be super duper close to our correct right answer, but I hope that you feel comfortable with the process that we are doing right here. And I hope that you agree with me that you would probably literally learn to program than do like a 100-step version of this to get a good answer, right? So I hope that we're all on the same page with that. So we've come up with our by hand approximation. So before we go to start writing code, the other thing we want to do is this. Let's compare to the exact answer. Let's get the exact answer to this guy right here. We want to find y of 1 given this initial value problem. Let's go do that, and then let's see if we can write code to mimic all this stuff, to generate some graphs, all that kind of good stuff. And by the way, I just want to say one other thing right here, is that what I'm picturing happening here is this. Let's draw actually a pretty good graph of what we are going to expect to see once we produce our graphs here in a moment. We're graphing the stuff in the ty plane, and what I know is that I am interested in time gaps of delta t, right? So what I'm picturing here is we said that, and maybe I'll go up to like 8 right there. So there's 1. So we started right there. There's our initial condition. That's y sub 0. We then updated and we got up to 1.75, but notice that we did that by traveling in a perfectly straight line. Then we updated again and we got up to almost 3. Right? And notice we were a little bit steeper right there. It's hard for me to draw that well, but we were a little bit steeper right there. Then we updated again. We got up to 4.5. And we updated again and we got up to 7. So, and I want to say 2 things here. One, I want to label these. This is our y0. That's our y1. That's our y2. That was our y3. And this is our y4. And because that was a 4-step problem, that's our final y value that we were estimating. And here's the important thing that's really hard to see with the graph that I just drew. That these are all straight line pieces. Right? I know it kind of actually looks like a curve right there. It's not. I just drew perfectly straight lines between each of those. We're truly following a linear, all vectors are linear. We're truly following a linear vector here for a certain amount of time, 0.25 seconds at whatever the slope is that we've been instructed to move. So notice here in this graph, when we go to produce our graph here in a minute, you should be expecting to see this looking sort of like a piecewise function, where it's going to be like sort of like an angle that we're going to see right there, where it suddenly changes direction rather than smoothly changing direction. But because this is either your 3rd or your 4th calculus class, I know that you can visualize what's happening here. As we keep the 0 to 1 interval, but as we increase the number of steps from 4 up to like 40, we're now getting a bunch of very short straight lines. And then as it goes from 40 to 400, you can't even tell that it's not a smooth curve anymore, because all those lines are now going to be 0.0025 units long, or whatever it's going to be out there, or maybe that's for 4,000, whatever. The point is, the number of subintervals increases, the approximation should get closer and closer to the true curve that we're expecting to approximate. Right? So let's go ahead and get our exact answer here, and then let's start writing some code. So we've got dy dt equals 2y plus 1. It clearly is linear. Dy dt minus 2y equals 1. It looks like our integrating factor here, mu, is going to be e to the integral of negative 2 dt, which is e to the negative 2t. Right? So I'm going to multiply everything by that. So we should get here then a e to the negative 2t dy dt minus 2 e to the negative 2t y. And again, notice I'm doing this thing I always do, which is when I multiply here, I do a very unnatural thing, which is I'm jamming my integrating factor in between the negative 2 and the y. But that's because in my mind, this is one term right here. This is the derivative of e to the negative 2t. So I'm organizing this to force this to look like an output from the product rule as hard as I can. Don't forget to multiply by your integrating factor on the right. I forget, that's like my most common mistake in these, is I forget my multiplication on the right. This pretty clearly looks to me like the derivative of y e to the negative 2t, since I've seen enough of these by now. And so now we can go ahead and integrate on both sides. And what are we getting right here? We're getting y e to the negative 2t equals, and here I'm going to, it looks like I'm going to get a negative 1/2 e to the negative 2t plus c. It seems like I want to multiply everything by e to the positive 2t, so I'm just going to get a negative 1/2 plus c e to the negative 2t. And when I go to, now I want to evaluate this at my initial condition right here. I actually need to get that guy. And so if I plug in my initial condition right here, what was our initial condition? Y of 0 equals 1. When I plug in 0 here, I'm just getting 1, right? So I'm going to add the 1/2 to the other side, and I'm getting 3/2 equals c. And so let me get this guy out of the way here. It looks like our exact answer then should be that we're getting, I almost got it all in right here, is y of t equals, I am seeing our final answer of negative 1/2 plus 3/2 e to the negative 2t, which we might want to rewrite as 3e to the negative 2t minus 1 all over 2. Right? That's my y of t right there. All I did was add these because they have a common denominator of 2 and put the positive term first, the 3 first, the negative 1 second. And what we know that we are interested in is y at 1. So this is our comparison now. This is our particular solution. This is the curve that we just imitated with those straight lines. What I wanted to know is what number should we have gotten for y of 1 if this approximation was perfect? Well, this should just be 3e to the negative 2 minus 1 over 2. Let's go to our calculator and check. 3e to the negative 2 minus 1. And we're dividing this guy by, oh, wait a minute, what am I? Oh, I see the thing that I did right here. I made the same mistake that I've made so many times before. I'm sitting here talking to you guys, bragging about how I didn't forget to multiply by my integrating factor over here. But notice that when I multiplied by e to the positive 2t right here, I actually wrote it again as a negative 2t right there. That was my mistake right there. Let me go back and fix this, right? I need to cancel e to the negative 2t with e to the positive 2t. So that should be e to the positive 2t right there. So let me erase that. That still is going to be the same for c. But coming down here, we're going to erase that negative. We're going to erase this negative. We're going to erase this negative. Okay, now let's go and get our solution right here. This should be 3e squared minus 1 all divided by 2, and I am getting 10.5834. So kind of what we're seeing here is this. We approximated the value to be like a little over 7 using Newton's method. We found the exact answer to be close to like 10.5, so not super close, off by like 50%, right? But what you guys know from doing all of our Riemann sums and stuff like that is, if you ever do a Riemann sum with only 4 rectangles, then what the heck are you even doing, right? Like it's technically a good conceptual thing to do. I didn't expect to get a great answer here. 4 steps is way too like discrete of a step size for me there. So that was, I wasn't anticipating getting a great result from that guy right now. So what we want to do is we want to do kind of 2 important things, which is 1, can we reproduce exactly what we got right here? In Python, and if we were to exactly reproduce it, could we then use that same code to greatly improve the approximation? So the 2 things that I now want to do is go write code to do 2 things. 1, can we get this number back out from writing code so that we can get a confirmation that the code that we're writing mimics the work that we did by hand? Then we want to ask, can we just increase the number of steps from 4 to something else to get closer and closer and closer to this number that we know to be the correct number, and ask ourselves, like, how many steps do we really think this is going to take? How many, this is like asking the question, how many rectangles should you break your Riemann sum down into until your approximation of the integral is actually really close to the actual value of the integral? Same type of question here. The third thing that we're going to want to do is I want to say, I know what this true solution curve looks like. That is the graph of the true correct answer right there. What I want to know is, how does this approximation graph compare to the true solution graph. And before we go over there and do that, I kind of want to point out to you, I have a good guess for this. What I can see is that we should be graphing, and I'm going to scroll again, I know I've been doing a lot of scrolling right here. This should be a function that is increasing and concave up. That's what my exponential functions do. This is essentially just e to the t, right? So it should be increasing and concave up. What I know is going to happen is every time Newton's method looks at a vector over here, it's going to see some direction of motion, a tangent vector essentially. It's always going to be underneath this curve because it's increasing and concave up, right? Every single tangent vector is going to live completely underneath the curve. So what I'm expecting, and I kind of confirm this here, is that my solutions are underestimates, my approximations I should say, are underestimates of the true solution value because the function that we're approximating is an increasing concave up function. So I'm picturing that these are all really like tangent vectors relative to the true curve. And since this is a concave up and increasing curve, they're all going to live underneath it. So I'm expecting my actual curve to be like above it, but also have that kind of exponential type shape right there. I want to produce both of those graphs so that we can visually see that comparison. Let's go do all of those things right now. I've been waiting for this for a month. Okay, so let's do the dang thing here. So, oh, don't do that to me. I'm trying to set up my stuff over here. So, here is what I'm doing. So what I'm going to do is this. I have Jupyter Notebook. I have moved it to be down here on like my functions down here. When I open up my Microsoft menu, when I click in the lower left corner, like the start menu down there, there is a folder in there that says Anaconda 3. And when I open that folder, I can see Jupyter Notebook. That's all I'm clicking on right there. I've dragged it down to be like a thing I can click on as like a start button, like next to my Google Chrome button, stuff like that. But the point is, when you open Jupyter Notebook, you should see a small black window open up with some like old terminal style stuff from that looks like it's from 20 years ago. Don't close that thing. That has to be running. What that's doing is it's creating a virtual server on your computer, which is helping it be like a communication to Jupyter Notebook. So you're technically sending all of your stuff to that black window. That black window is asking Python to do all these stuff, and it's the thing that's spitting it back. So that's kind of managing your Jupyter relationship to Python right here, which is a little bit weird. But anyway, don't click the X on that black box. If you do, then just close out the window that we got right here and restart the thing over again. So what you should have now is you should have a Jupyter window that looks like this. And importantly, it's in browser. Jupyter is always going to run in browser. So I want to show you guys also that I don't directly use Jupyter Notebook. I actually typically use Jupyter Lab, which is the slightly newer version of Jupyter Notebook. The historical sequence of this is this Jupyter project, and remember, Julia stands for, Julia stands, or excuse me, that's what I was getting wrong. Jupyter stands for Julia, Python, R. Those are like three of the biggest languages used in all of scientific computing that there is, science and stats. Those are the three biggest ones. So Jupyter is really an acronym of three programming languages. The Jupyter project started out being referred to as Iron Python until it started to incorporate all these other languages, which is why they changed the name to Jupyter. Iron Python is where we got this acronym IPYNB. That is an Iron Python notebook. That's where the suffix came from, is Iron Python. That all ended like early 2000s when they transitioned into the now what is referred to as the Jupyter project, but that's where that IPYNB came from. The Jupyter Notebook thing was a really good idea, but they sort of realized a couple of years ago, 4 or 5 years ago, that they sort of started building this on some slightly less than desirable architecture that they were not going to be able to like just change with a new version. So they had to create a new thing that's called Jupyter Lab to make that happen. So Jupyter Lab is sort of like the most modern version of Jupyter, but lots of stuff is still in the notebook version versus the lab version. I'll show you how to switch back and forth between the two. So it might be the case, I'm not 100% sure on this. I'm pretty sure that if you have Jupyter Notebook, then you have Jupyter Lab, but just in case it's not, I want to show you both ways. We want to get a new notebook either way. If you are currently looking at the screen I'm looking at, then you can click New and click Python 3, and it's going to bust open a new tab right here for you where you can start writing code. I kind of don't like the fact that then this gives me like a whole bunch of tabs up there if I'm doing a whole bunch of things. So that is one of the two drawbacks to using original Jupyter notebooks. So what I'm going to do is I'm going to show you how to do something slightly different here. I'm going to close this one because that was just a specific file I was working on and not Jupyter collectively. I've still got my base thing right here. Up here where it says tree, I'm going to get rid of tree and I'm going to just type in lab and I'm going to hit enter. And what it's going to do is it's going to take me to an alternate version of Jupyter Notebook right here, the lab version instead of the classic notebook version. I kind of like this one better. This one does a couple things for us. One, notice that there are now tabs within your browser tab. So one good thing here is now you have one primary Jupyter Notebook or Jupyter Lab tab in which you might have 20 open files, but those will all be their own tabs within this thing. So rather than getting, like the classic like Google Chrome with 40 tabs open thing, there's now one tab that represents all of your Jupyter stuff. And in it, you might have multiple projects that are open at once, multiple files open at once, but that's all self-contained. So what I can do now is I can either just click here to open my new Python 3 notebook, or the other thing is that you can click this plus symbol up here for a new launcher. But notice a launcher just gave me another one right here, right? This plus sign really just opens up this window right here. So I've already got that window. So I'm going to click here, and notice it takes me to something that looks just like we saw 1 second ago. I'm going to show you one of the nice benefits to using the lab that we don't get with the notebook thing is this. One of the things that's really handy here is I can drag and drop different cells to be in different orders. That is one of the features that is only associated with Jupyter Lab and not with Jupyter Notebook. And I am constantly rearranging my work, so this is like a valuable thing to me. Also, I typically don't like seeing my like navigation menu over here all the time, but I could just click on this folder right here and it'll tighten that up. And if you want to see it again, you can just keep on clicking it to open it and close it right there. I think I want to increase the size of my window here so you guys can see what I'm writing a little bit clearer right there. Cool. So let's do a couple things here to kind of get started, since this is going to be the real first code probably that for a bunch of us that we're ever writing. A couple things up here. We clearly got a save button right there for all of you that don't recognize floppy disks because those are 30 years old by now. This plus sign is going to insert a new cell below the cell that we're currently looking at, right? So I could click plus a bunch of times and there's now a bunch of new places that I can write code. Get rid of this stuff right here. The scissors will cut the selected ones, but you need to be careful because I'm pretty sure that you can't get them back. This is like a permanently delete that cell, right? So if you've got extra ones of stuff you don't need anymore, you can cut them. Be careful with that right there though. Here is our copying of a cell. So if we want to like kind of, and this is a very typical thing to do, we want to do essentially the same thing, but we want to modify some parts, but we don't want to get rid of our old code. We can copy a cell and then drag it to a new location in the notebook, lightly modify it for our new purposes. This is a pretty common usage right here. And then this is our pasting of the cells right here. We've got our play button right here, which will run the code in the selected cell. The stop button, which hopefully we never need, which will say, hey, stop running the code. All the code that we're going to run is probably going to run so fast you couldn't even stop it partway through if you wanted to. But if it ever ends up being the case in your code writing life that you end up in an infinite loop where your code is just running forever, the stop button will stop it for us right here. I never use, I don't even know what the restart the kernel. There's different ways to do that, and restart the kernel, rerun. I never really use these. In fact, I really never use any of these 4 buttons right here. There's other ways to do this stuff. So let's do a few things here before we write any code. Another thing you should notice is that there's a code drop-down box right here. This is one of those stupid things. The way that I'm sharing my screen, you can't see that I'm highlighting other selections right now. But our 3 choices here are code, markdown, and raw. Markdown is where you can just kind of write some stuff, right? So I can do some stuff right here. I want to run this cell to evaluate the markdown code that's in it. And to do this, I'm going to press Shift-Enter. Shift-Enter has essentially evaluated that. Now notice this code, this block right here is a code cell. So if I type the same thing of some stuff and I Shift-Enter this guy, it's going to say, I don't know what you mean. That's not valid Python syntax. That's because it's interpreting this as Python code because this is in a code cell. If I switch this to being a markdown cell, then I could run it and it would just say some stuff again. It's got no problem with that because markdown just means write some stuff in English right there. All right. So notice each individual cell is either code, markdown, or raw. I never use raw for anything. I don't really know what its benefit is over markdown right there. So what I think we should do first is we should be some responsible code writers. By the way, I'm just going to cut this one since I don't need it. I'm going to double click on this cell to get it back into edit mode right there. And I'm going to give myself a, sort of like a title for this, right? One of the cool things we can do in Markdown is we can use a bunch of Markdown syntax. Also, if you know any HTML, that is going to work in here. This will evaluate HTML. Also, if you know any LaTeX, this will evaluate LaTeX things. So here's some stuff I want to write. One, a Markdown command. Using these pound symbols will give us headers. This is the header sizes. So I'm going to do Euler's method. And notice I put 2 pound signs in front. Now when I evaluate it, it's nice and big. If I do only 1, it's even bigger. If I do like 5, it's smaller out there. It's basically just bold at this point, right? So this controls a size of a header, where this is like your maximum size header, and the more of them you do out to 5 will make them smaller and smaller. By the way, if it's touching this, it's not interpreting those pound signs as a header indicator, so there has to be that space right there. And remember, I'm doing Shift-Enter when I run my code each time, or you could simply click the play button, which will run the selected cell to get it in the format that you want. So I'm going to go and make this a pretty big header size right there, Euler's method. And then what I want to do is I want to say the problem that we're doing. What are we trying to do? Ooh. So I want to approximate the solution to an initial value problem. Well, I'm going to teach you all a smidge of LaTeX right now so we can write some fancy math formatting stuff. What I would like to do is I would like to straight up have exactly this right here. I want literally exactly that to be written in there, and I need some slightly fancy formatting things to get things like a fraction in here. We can also do this to get like integral symbols, other stuff, subscripts, some nice stuff like that. So we want dy dt equals 2y plus 1, evaluated at y of 0 equals 1. Let's see if we can type this in LaTeX formatting. And again, these are kind of our like little bonus topics for today, but these are small things that are kind of relatively easy to pick up little pieces here and there. So there's no reason not to do this. So to format some LaTeX stuff, which is your fancy math formatting, everything needs to be surrounded by dollar signs to indicate that we're doing math mode in LaTeX, and it'll automatically do this for you. So what I want to do is I want to create a fraction. I'm going to use the fraction command, which is our /frac. You should notice it's in green right here, so it's recognizing it as a function. LaTeX uses curly braces, not parentheses or brackets, as its general grouping symbol. So the first thing of my fraction is the numerator, that's dy, close that grouping up. The second part is dt, I'm going to close that one up. And just to see that this works right now, notice I've started and ended with a dollar sign. If you don't end with that dollar sign, it's going to be mad at you. And it's got a nice little dy dt right there for us now in math mode. If you don't include a dollar sign, it's just going to be like, I don't know what the heck that is, and it's just going to give you the raw version of it right there. Right? So dy dt equals 2y plus 1. I don't need anything special for that, like a times symbol right there. And then the other thing that I feel like I need right here is I want to have maybe like our y of 0 equals 1. That's the full initial value problem right there. So there we go. So we have our nice math formatted version of this right here. One thing that's a bit obnoxious in LaTeX is this. Say that you decide that you wanted more spaces right there. It just ignores that. And that introducing horizontal spacing and vertical spacing in LaTeX is kind of obnoxious. It doesn't just do spaces and tabs and enters for new lines. One thing that we can do, this is kind of annoying here, I don't even know why that's the name for it, but the expression quad will give you like I think quad is like a tab. I think quad is representing 4 space characters. So that now does give us some spacing right there. That's some dumb stuff right there. That kind of annoys me right here. But in any event, I think that we've got a nice little header for ourselves. What are we doing with our code? We used the pound signs to make a header for Euler's method. We described the problem, and we described the problem using some LaTeX code in math mode right there. Math mode always indicated with those dollar signs right there. So this is our way that we can type math out. And so again, you can see you can look up everything relating to LaTeX here. How do I make this symbol in LaTeX? I have Googled for LaTeX about 1,000,000,000 times in my life. Tons of great sites that'll help you out with that kind of stuff right there. So again, I'm going to shift enter to run this cell. If I ever want to come back and modify it, remember, I'm just double clicking on this evaluated cell and it takes it back to edit mode, or you can click play to get it back to evaluated mode right there. So we're ready to actually write some code. So before I do this, I just kind of want to show you a couple brief things right here. One, I'm going to put a ton of comments in my code. Comments in programming are things that are not run as code. They're just meant to be read by the reader, by somebody else using the code. They're not actually code itself. So comments are indicated with the pound sign. So this is a phrase that if I were to run this without the pound sign, it's getting all upset. Notice it's even highlighting with, because with is a special Python word. And it's like, I don't know what the heck you're talking about, but all I got to do is throw a pound sign in front. And it's like, it just ignored everything because that line started with pound. And here, this one doesn't care if there's a space or not with that right there, whatever. So comments are indicated with a pound sign. And what we're going to do today is we're going to define a bunch of variables that are of interest to us. So I'm going to define a couple things right here. I could make some phrases like x is 3, y is 5. And I can run that. And notice that nothing happened right there. That's because I didn't ask for any output back from Python here. What I might want to see is things like, what is x plus y? Well, Python has a value for x and has a value for y of 3 and 5. So when we run this, we expect to get 8. We're highly satisfied that it seems like our stuff's running right here, right? Now notice, though, if we do x plus y plus z, from the algebra that you know, you might be hoping to see the expression 8 plus z. But unfortunately, Python is not down with symbolic stuff like that. It's saying to you, like, I don't know what z is. There's got to be some defined thing. If you're going to use z as a variable, it's not just going to say, and plus whatever z is, because the issue here is that we think of variables as values that numbers can take on. But in Python, a variable could be anything, right? So maybe I want to define something to be like a list. Well, I can make a list. Let's call it z. Lists in Python are always going to be indicated with brackets, right? So your brackets that are sitting below your backspace symbol right there. So I could make a list of things that looks like 4, 5, the word cat in quotes right there. That's a list. A really nice thing in Python is that lists aren't required to be all of the same type of information, right? That was 2 integers, or ints, according to Python. In fact, let's change it up here. 5.2, 4, 5.2 cat. That's the list. I run it, Python's totally cool with it. I can ask Python some questions like, hey, what's z? It's going to tell me back the list that I gave it before. Here's some other really important things we're going to do today. I just want to show you a couple more operations and then we're going to do our Newton's method stuff. One thing that we can do with lists is we can append things to them. So I can say, take the list z and append to z, stick on to the end. I don't know, let's put dog on the end of the list right here. If I do this, I can run it. Python didn't yell at me, but it didn't tell me anything. But now I can go say, now what does z look like? Well, now it has dog on the end of the list. That's kind of cool. So we can build lists manually, but we can also one by one attach things to lists. That's going to be really important for us here today. Other things that we can do is we can ask for objects that are within the list. So z is a list. And therefore, I can use brackets on the end to indicate which item in the list I want. Python is a zero-based indexing language, which means the 0th item in the list will be the first. This should be giving me 4, because 4 is the first item in the list. It's at index 0, and if I run it, I do in fact get 4. Notice that 0, 1, 2, 3 means that even though the length of that list is 4, that's a different 4 right there. Ooh, that's confusing right there. The length of the list is 4. There's 4 objects in it right there. Notice that if I tried to ask for the 4th index, I'm going to get an error. It's going to say that's beyond the range of the index right here because the real index values are 0, 1, 2, and 3 if there's 4 objects in your list, because it's always going to start counting at 0. So one thing you might wonder is, how do we get the last thing in the list then without counting? Well, a cool thing that Python does that other languages don't do with their list is it can handle backwards counting. So if 0 is the first thing in the list, then -1 loops around and grabs the last thing in the list. -2 would give us the second to last thing in the list right there. Right? So Python can count one loop forwards and one loop backwards if you are trying to grab an object from a list right there. This will be useful to us because we're going to want to know what was the final y value of our approximation, right? Like when we were over here in Microsoft Word, we were getting our things that looked like our y0, y1, y2, y3, y4. Well, we're going to make a list of all of the y values. We're going to one by one append the newly created y value, and at the very end, the object of interest will be the last thing that we put in the list. That will be our final approximation. So some list stuff is going to be relevant for us here, but it's relatively simple. And honestly, it's probably annoying to you if you've actually done programming in any other language before, because most other programming languages have restrictions like you can't have mixed data types within your lists. You can't backwards index with your lists, stuff like that. Python's a little bit, it's almost friendly to the point of being difficult to understand for people that have a lot of programming experience here. So if you're new to this, hopefully this is kind of quick and easy for you. So I'm going to get rid of all this because none of this is relevant to our Euler's method, but you can see some things we're going to do. Comments are always indicated by starting the line at the pound sign. The whole comment, the whole line gets ignored after that. We're going to make a lot of variables, including some of our variables are going to be lists. We're going to add on things to the lists one at a time, and we're going to want to grab last entries in a list, which we can always do by indexing the -1th item, the one counting backwards. So looping back around, viewing the list as a cyclical thing rather than as a linear thing. We'll grab the last item that way. So let me get rid of all this stuff here by cut, 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 cut. And I'm going to bust open for myself a whole bunch of cells because we're about to do a bunch of things right here. So we're trying to do some Newton's method things right here. So what we need to do, and again, I'm going to pop back over to Word and see what it is we need to define. Here's the things I'm thinking that we need to define. To define our scenario here for Newton's method, here's the things that I see that we need. We need to know an A and a B, an initial and, oh, by the way, let me say one more thing. We want to write code that is very easy to alter later. What I don't want to do is to write code that's very specific to this one problem. I want it to be trivially easy for me to change my bounds to be from 4 to 7 instead of 0 to 1, and me literally just have to change two numbers 4 and 7 for variables A and B, and for no other work to be needed, right? So what we really want is to define everything as a variable so that we can modify those variables and just change one thing and all the rest of our work gets auto-updated for us, right? So we want to define some variables for things like, I need to know A, B, my initial final times. I want to know N, the number of breakdowns. Based on A, B, and N, we want to compute our delta T. I want a function that does that math for me. I need to initialize an initial value for Y, a Y sub 0. I'm going to want to store all of these times in a list so that we can graph this chord. Notice that out here, all these points are ty pairs. So I'm going to want to get a list of all of our t values and a list of all these y values so that I can plot them as ordered pairs eventually. So I need a list for all my t's and a list for all my y's out there, right? So there's a bunch of variables that we want to define to start. Then we will use those variables in our Euler's method computation right here. So let's go ahead and define a whole bunch of those things that we're seeing that we need here. So what is it that we want to define? Well, first thing I think we should do is let's define our f of y function, right? So in Python, we can define our own new function that will take in stuff and spit out stuff, just like a function in algebra with the def marker right there. And by the way, I'm going to give myself a comment here. I'm going to define the function of the differential equation, right? So what do we want to call it? Well, let's just call it some really generic name that we're used to using, like f is going to be the function's name. What type of information does f need to take in? If this is my f function right here, well, it looks like it needs y. I want to give you another thought here as far as building like a nice robust program for ourselves. What I'm kind of thinking is later we might want to look at more complicated functions that might not be autonomous like this one is. This one has no t's in it, but you know it would be completely not weird for me at all to do 2y plus t as my differential equation, right? So I'm thinking it's plausible that there could be t's and y's that we might need for our input here. So let's be robust and do that. I'm going to build a function that takes in t's and y's. We must have a colon at the end to indicate that we're going to start our definition. And very importantly, notice when I pressed enter, it was auto-tabbed in one indent right here. Python really cares about things like those indentations, so leave that right where it's at right there. It's got to look kind of exactly like that. That colon has to be there, def has to be there, def has to be lowercase. Notice F is in blue. This we could call whatever the heck we want. We know that we're gonna want inputs of t and y, and what do we want to get out from the function? Well, our output is what we want to return. What do we want the function to give back to us? That's the return value right here. What we want it to give back to us is 2 times y plus 1 right there. Some small things right here. 1, you cannot just do 2y. It does not know that you are indicating multiplication. You have to indicate all multiplication in Python. 2, you do not need these spacings here, and this does not need to be no spacings here. I just try to indicate this as the way that I write my math, which is that multiplication is like numbers adjacent, but I usually like my addition to indicate like different terms, so I usually use spaces there. So this spacing that I've done here is a personal preference spacing and nothing else, right? So this function should take in a t into y, and it should spit out whatever 2 times y plus 1 is going to be. This is going to compute all of our function values for us right here. And again, notice this is a really simple function, but we might want to later do much, much more complicated things. And what you want is you want to just have to go in and just alter this and nothing else to get your new outputs rather than having to build a new function for yourself. So we're thinking about doing favors for ourselves in the future, not just doing one problem that we want to do right now. So I'm going to go ahead and shift enter this guy, and what I want to do is I want to test our function. So let's try some outputs here. One thing I'm thinking to myself here is this. Notice that we have defined this so that we have to give 2 inputs. You can't just ask for f of 1, because if you do, it's going to give you an error, and it's going to say it's missing 1 required positional argument. It thinks that the one that you gave it was just t, and that it's missing the positional argument for y, argument being the input into a function. So this function, because we gave it 2 things right here, and again, we could have just done that, so it was an f of y function, in which case that would work to give us 3. I'm trying to think ahead though, right? I'm trying to think to myself, let's do ourselves some favors here for the future and build this robustly. So this is going to say time is 0, y is 1. By the way, I got to rerun that to re-update my definition here. If you ever modify any of these parts up here, you need to rerun the cell so it gets the new version of that stuff. I almost forgot to do that right here. And there's no risk in rerunning it, whatever. I can just rerun this over and over and over. It's just relearning that function over and over again. So here we're seeing, yeah, if you use a y value of 1, then you should certainly be getting 3 for dy dt right there. So I'm reasonably convinced. F of ty. So I gave it and notice here again, it's obvious that time didn't have any input on this stuff, right? Any impact on this. So it doesn't matter what time we give it. It's going to be, it doesn't matter because it's not being used in the computation for the return function right there. Only the y was affecting our outputs, and so the y value of 1 was the only thing that influenced the output that we got. That should make a bunch of sense right there. A little bit complicated, but again, this looks like algebra to me. F of ty, that's a function, and since t had no bearing on the outputs, I changed t and my output didn't change. Only the y value of 1 is what changed, right? Cool. And again, if we made this t, then now it should matter. What should we be getting if I update my function to look like this? Now it should be 2 times 1 plus 10, so I should now be getting 12. And we do get 12 right there, right? So, and again, if you modify this to change this, recognize I didn't just arrow down to get to my new cell. I'm shift entering every time to rerun that cell to update my new expression for the differential equation. So I'll change this back to 1, shift enter to run it, and then back here to get back to the 3. And also notice over here, you can tell that these cells have been run and in what order they've been run. This is the 34th output so far in this collective notebook. 35th input, 35th output right there from the notebook overall. We can see those things right there. Cool. So we've defined our function. Now let's define all of our variables required. So here's some things I'm thinking that we need. We need an A, we need a B. That's our time interval. We need an N, our number of steps that we want to do. And we're going to want a delta t, which I'll call dt. And I'm going to get really explicit with this right here. I probably wouldn't go so heavy on my comments normally, but I'm going to do that here to make sure that we all have the kind of help we need here. Right, so here's some things we want. We know that we're going to start at time 0. We're going to end at time 1. So those were the given constraints of the problem, is that we were given an initial condition at time 0. Our goal was to find time 1, so that's what I made b. We were told, because we're trying to mimic our by hand work right now, that we want 4 subintervals. And we know that the way that we compute dt, and so here's a place where I want to say again, do friendly favors for yourself. If you put 0.25 right here, you're screwing yourself over for later. We don't want to do that. I want to think that dt is just based on a, b, and n, and I want to easily be able to change n to 400, and I don't want to have to change anything else. So I am going to make my dt be based on my a's, b's, and n's, and I know how to do this. b minus a over n. That's how we compute delta t. It's exactly what we did by hand, but in this case now, it will use the previously defined values of b, a, and n to compute dt. So let's go ahead and run this and see that we get some things that we expect. And I'm just going to do a, b, n, dt. Those are the 4 things, and it's telling me, yeah, 0, 1, 4, and 0.25 satisfactorily is exactly what we were expecting to get for these guys right here. So let's just say check right there, and we checked that that stuff worked right there. So what other values are of interest to us right here? Well, some other things that we saw that we're going to want is that we're going to want to establish our initial y value. So that I'm going to call that y0. And we were told that y of 0 is going to be 1. Right? The other thing I want to do is I want to build some lists that are going to eventually hold all the t values that we see and all the y values that we see, so that those 2 lists together form a table of ordered pairs that are effectively going to be the points that we're going to plot to produce the graphs. All right. So to make the graphs, we're going to have to give Python some lists of ordered pairs. We want to build those lists that are going to be representative of those things. So I'm going to make what I'm going to call a t list here. Ooh, and by the way, we also apparently need an initial time. We know that we're going to start at time 0 right there, right? So, and we could start at other initial times, which is why I'm calling that a variable. So I'm using that y0 and t0 as my just names for a variable. I'm picturing that as like y sub 0 and t sub 0 there, right? So let's build our lists. I'm going to name these things t list and y list just so that I can remember. You don't need to use that naming convention right there, but I think it's a smart thing for me to do to remember that this variable represents a list, not like a number or something like that. Remember that lists are always indicated with brackets in Python. It would be completely acceptable for us to just run this as is. An empty list is fine, but I know the one thing that should be in the list so far, which is t sub 0. So we're starting the list with its first known object. Similarly, our y lists, currently we only know one y value of interest to us. It's y0. So I'm starting my lists and I'm putting the first thing in them. All right. I'm going to go ahead and run this guy right here. And again, I'm going to just check some stuff to make sure this is doing what I want. Let's check what our t list looks like and our y list. And look, notice here it did something that looks different than right here. This was a sort of like, we asked it for 4 things, so it gave us 4 things in parentheses. Here we asked for 2 things, so it gave us 2 things in parentheses, but each of those things itself was a list in brackets. That's good that those brackets are there. It's indicating that Python is clearly aware that those are in fact lists. It's a list of one item, but we're going to append more things into the lists as we create them, right? So it seems to me like we know most of the stuff that we want to deal with here, right? So now let's actually do Newton's method. I'm going to, instead of just using a generic little comment right here to describe what I'm doing, I'm going to bust out a markdown cell instead for myself. I'm not going to make my header quite as big as before, so I'm going to do the 4th size of header, so a little bit smaller. And let's go ahead and do some Newton's method here. And now we get nice little headings in there. That's so nice right here. And so it generated for me a new cell. I'm clearly feeling out that I'm probably going to need some more cells here also, so I'll click the plus sign, get some new ones right there. So let's go ahead and do the thing. One last thing I want to do is some new variables before I go to actually do Newton's method is this. We currently have variables for the initial value of y and the initial value of t. I kind of want more generic variables to hold just what is t currently and what is y currently at this layer of Newton's method. So I'm going to make some just generic y's and t's. And those are going to hold the one that we're at so far. So these will be our T6, our T14, our Y9. Those are going to be held by just a more generic Y and T. And I know what I want them to start as. And again, notice that every time I define a new variable, I am hoping that I can reference it based on a previous variable, or it's one of the variables I actually want to change, so that I don't have to do work to update this later when I want to find Newton's method for other things, if I want to change the conditions of this problem. So what I'm going to do here is just like what I said before, which is I'm going to say, what is t right now? What is t right now? Well, I want it to be whatever t0 is right now, because that's where we start. What is y right now? Right now, y is its starting value of y0. But the point is this. I'm never going to change t0 and y0 throughout this Newton's method. I am going to constantly update what t and y are throughout the Newton's method. It will constantly update to be the new value of t, the new value of y each layer. So what we know that we want to do is that we know that we want to, flipping back over to Word, is that we know that we want to repeat a process over and over and over again. And the only thing that's going to change is we're going to, instead of using y0, we're going to use y1. Instead of using t1, we're going to use t2, stuff like that. That's all that's going to change. The actual computation is going to be the same. So let's go ahead and make that happen over here. So what I need to do is I need to get a way to repeat a process over and over and over again. This for loop is going to do that for us. So a for loop will repeat the same few lines of code some specified number of times, or for a specified list of objects, or an iterable type of objects that are out there, right? So what we're going to do is this. We're going to make a for loop here. And so what I want to say is for what? For each step in the Newton's method process. So I'm going to say that. For step, I'm making up a new variable now that's called step. It's not, we're not actually going to use it, but for each step in the process, how many steps do we want to do in this process? We actually know that already, right? We have decided that n is the number of steps that we're doing. So this is saying do Newton's method 4 times. I'm just trying to say that right here. For step in the range of n, right? So the range of n is 0, 1, 2, 3. 0, 1, 2, 3 are the 4 values that step will take on. So this will say repeat this code n times. What code is it repeating? Watch, because I indicated a colon at the end, right? A for loop is always going to be ended with a colon to start the for block. When I press enter, it's got me already indented right there because everything in the for loop has to be that one tab in, and Jupyter will be very nice and will help you with that indentation. So it's supposed to be indented like this. So what is it that we want to do here, right? What we want to do is we want to update what y is, and then we want to save our new y and t values that we've got. So we want to update y and t. All right. So updating t and y, I'll just put them in order right there. We know that we want to compute our new value of y, right? So we're going to update y. So what we're going to do is we're going to overwrite the old value of y. We've already tracked y0 being in our y list. The next y I care about is the next one, right? So how are we going to compute the new value of y? Well, what we're going to do is we're going to take the old value of y, which I'm representing with y right here. We're going to add on to it the slope of our curve at that point. We wrote a function that does this. What function? The f of t y function. This is the slope that we have when we're at that given y t value, right? So the slope is just whatever we get from f of t comma y. I can straight up write this with t and y because t is defined as a number. Y is defined as a number. It's going to compute a number for f of ty, and what do we want to do with it? We want to multiply it by our delta t, which we called the variable dt. The reason this line of code works with only variables is because every one of those variables has been previously defined above in a previously run cell. All right. So what this should do is it should do the updating. So now y has taken on the value of y1, having used the information from y0 and y0 and t0 right there, right? The other thing we're going to want to do is we're now going to say, by the way, what t value are you now at after that amount of time? Well, I need to make t bigger by delta t, right? We should have gone from 0 to 0.25. So what I'm going to do is I'm also going to update t. So what do I want to do with t? Well, I'm going to do t equals t plus delta t. Our new t value is the old t value plus the change in t. And by the way, I'm going to show you a different notation we can use for this. Since it's so common in programming to update a variable based on what the previous value was, a typical thing to do here is to use the notation plus equals. That will say increment by delta t. So that will say add on to the value. That says increase the value that the variable currently has by this amount. And by the way, in Python, minus equals, times equals, divide equals all work that way as alter the value of the variable rather than set the value of the variable right there. So two different ways. Notice we could totally write this one as y plus equals f of ty times dt. I just really want this to look exactly like Newton's method, so I'm going to leave it in that format right there. So here's the point. Now y and t are both y1 and t1, no longer y0 and t0, because those two lines of code have done the updates. What I now would like to do is save those values so I can use them to make a graph later. So what I want to do is I want to take my t list and my y list and stick our new values onto the end. So I'm going to do t list dot append, in parentheses, our new t value, t. Our y list also is going to append the value of y. So check out what happens in this for loop. We start at t0 and y0. We enter into the for loop, and the for loop knows it's going to pass through this block of code 4 times because n is 4 currently. If n was 400, it would just do this block of code 400 times. It's going to update y and t to their next value. It's going to store those values into their new lists as the last item in the lists, and then it's going to pop back to the top of the for loop to where it will then say, okay, update the values of y and t again based on their previous values. So this will give us y2 and t2 as we think of it, and it'll put those guys in the list. And it's going to do this for the number of times that we indicated, n times, 4 steps out there. I did create a variable in a sense right here by naming that step, but notice we never did a computation. It was never like, oh, if you're at the 7th iteration of Newton's method, then multiply by 7. Like that didn't come up, right? So technically I created a looping variable called step, but we never used it. A lot of times people will use an underscore to hold a variable, a looping variable that you have to create but that you never use, and the underscore indicates don't think about that thing, just know that for loop says do this stuff 4 times. Other times in for loops, you want to use what number loop you're in as part of your computation. If you're in the 6th pass through the loop, go to the 6th entry in a list or something like that. We're never doing stuff like that right here. So whatever, it doesn't matter. The point is, this could be that right there, and this code's still going to run the same. We're just creating a variable name of something generic right there, just because that's a requirement of the structure of this code. So what we want to do is we want to run this. It's going to do the 4 loops through the for loop right there. And what we should be able to do is go look at our y list. The last item in our y list, we're hoping matches that last item that we computed by hand. So I'm going to go ahead and shift enter this guy. Hopefully you don't get any errors like I didn't get any errors. If it worked, it worked. I mean, assuming that you've got the right math in there. If you've got some errors, you're going to see if you can figure out what those errors are indicating to you right there. Maybe you forgot your colon. Maybe you didn't use your appropriate spacing of 1 tab over here. Maybe you didn't have an equal sign that you needed to have, or you forgot that multiplication requires the asterisk right there. The point is we want to say, did we get it? And the way that I'm going to check is I want to see what's my y list look like. Oh yeah, Ooh, 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 that feels good right there. These are exactly the y values that we came up with by hand right there. So it looks like our program is doing exactly what we did by hand. But now here's the awesome part. We can now just alter any of these initial variables that we defined. We could alter our function. We have no different work to do. We would just rerun all of our cells. We can alter our bounds over the time. We don't need to alter anything else. If we change A and B, we just get those for A and B right there, and it will update everything else that we need. If we wanted to change our number of subintervals, that's the thing that's going to improve our accuracy right there. I could literally just change this number, rerun every cell after it, and we will have our new approximated value down here. So what I want to do is I want to increase the goodness of my approximation, but what I don't want to see is a Y list that has like, I don't know, I don't want it to output a list that's like 4,000 things in here if we're going to go that big. So what I want to do is be a little bit more careful and just look at the last thing in the list, in the Y list right there. There's the last thing. That's our sort of our final approximation at Y at time 1 right there. So let's go ahead and update our code now. All I have to do is just go change this 4 to, for example, 40, and I'm going to run, 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 and run. Now it did the for loop 40 times, still took essentially no time. Oh, we're now getting values like 10. Our goal was 10.58. We're still a little bit far off from that here. So maybe 40 steps wasn't even enough. Let's go make it bigger. Shift enter, shift enter, shift enter, shift enter, shift enter, shift enter, shift enter. We're getting closer. And let's make it 4,000. Oh, we're getting there. Oh, we're getting there. Oh, so 4,000. That's a lot of iterations. I hope you're down with the fact that we didn't want to do this by hand. But even 40,000 passes through that for loop is like nothing for your computer to do right here. Watch how little time it takes to do 40,000 passes through the for loop. Done. Instantaneous still, right? That's still nothing. And now we are sitting at, this is accurate to, let's see. Yeah, we're accurate to 3 decimal places right now. That 4th decimal place is still not matching our exact answer right there. But the point is, we just increased our number of subdivisions to get a much, much, much finer approximation of the real results, right? So for our last thing that I want to do today, what we need to do is we need to build a graph of this thing right here, right? We want to see what our solution looks like graphically. So there's something I want to do here, which is, this is sort of my like our first code ever thing. I want to just like extract the key components of this without all my comments so that we can write this in a little bit more of a compact build right here. So really what I'm going to do is I'm just going to do a whole bunch of copying and pasting right here. So I'm going to say it worked. So let's do some graphing and we'll call it a day for today. So I'm going to bring in everything here just into one cell. That now that we know what all these parts are doing, I'm just going to get all of it together into one cell right here. So I've got my A's and my B's. So this is my initializations, as a programmer would say right here. We're initializing all of our variables to be some desired quantity. I want to change this back to 4 because I want to see that chunky, crappy graph and watch it get better. I'm also realizing, by the way, there's probably one thing we should have done ever so slightly different, which is that our time 0 is really A, right? It's really whatever our initial time is that's right there. That T0 variable is maybe actually unnecessary. That was actually like a, I don't know, not something we needed to do right there. Cool. So now we make our generic ones here. So that was all of our initializations. And now we're creating our general variables that will change. And then we're doing our method. So now I'll make this one big block. All right, the do Newton method is the stuff that's happening down here. And I'm just going to get rid of like all of my other comments in here just so that this is like concise. We can see the comments up above describing the exact same code. So the point is this, I want to just be able to run this once right here, and the important thing that I want to get out now is a t list and a y list. This is essentially ordered pairs, right? Where it's like, this is an ordered pair, this is an ordered pair, this is an ordered pair, my first t and my first y, my second t and my second y, my third t and my third y. So what I want to do is I want to graph these guys. So what we need to do is we need to bring in a graphing library. The core of Python, which that's all we've used so far, has no way to graph things. But somebody has done an absolute mountain of work for us so that we can use functions that they have written, right? The plotting library that we want to use is called matplotlib, which is a really ridiculous name. And then even worse, we're actually using only a sub-library of it that we have to call as well. So what we need to do is we need to ask Python to recognize that there's other things that are on your computer that it currently isn't thinking about, because to bring in all those libraries would make Python have to think about way too much stuff that's not really necessary most of the time. So we need to say, Python, please pay attention to that one thing that I downloaded there. When I say when you downloaded it, it came with your Anaconda download. So you should have this if you did the Anaconda download. So I'm going to import the matplotlib.pyplot library. This is going to give us our graphing stuff. Matplotlib.pyplot. I don't want to have to use that name every time I ask it to do things for me, so I can give it its own name. I'm going to give it the name PLT. So when I say as, this is me renaming how I'll reference the library in my code. So from now on, every time you see PLT, that is us asking this library to do some graphing work for us, because Python directly doesn't know anything about graphs. Somebody had to write all that code to make the graphs happen. We're using that code. It's a massive group project to build this library. This is a pretty heavy stuff going on here underneath the hood, right? So typically import stuff, you stick this standalone. I'm going to go ahead and shift enter this guy. You should notice that asterisk hung out there for a second. It had to stop and think harder than it had to think through 40,000 lines of this. I'm pretty sure the matplotlib library is more on the order of like 1 million lines of code, not just 40,000. So a lot of stuff it had to think about to make that guy happen. Right? So here's the way plotting works in matplotlib. What it wants from you in our most simple format right here is this. I'm going to say, hey, plotting library, right? Because again, Python doesn't know how to plot stuff. So every plotting thing that we want to do is not that we're asking Python, where we don't have to like make a formal request. This is like you asking your neighbor to do a favor for you. So this is me saying, hey neighbor, will you do this for me? Rather than just you doing it yourself. So this is me saying, hey, matplotlib library that I have called PLT. What I want you to do for me is plot something. So I am asking the matplotlib library to plot something for us. The way that we're going to give it the information into this plotting function is we're first going to give it a list of all the inputs and then the list of all the outputs. So what it wants is basically like all your x values as a list, comma, all your y values as a list. And it will plot an x, y coordinate grid just like this. We're calling them t and y instead of x and y, but you should be thinking, what are all the, in an xy grid that's a bunch of xy points, it's not a list of ordered pairs. It's not like we're making a list where there's x comma y, x comma y, x comma y. It's that we're giving it two lists, all of the x's and then all of the y's, and it knows to partner them up, first with first, second with second, third with third, on down the line. Now I've asked it to create that graph, but I still need to tell it to show me the graph. Creating and showing are two different things. And it did technically what we asked. Now, let's say one cool thing that happened here. One, it worked, okay, and the second cool thing that happened is, if you look very carefully, you can see these corners happening right at the quarter intervals, right? That's at 0.25, that's at 0.5, that's at 0.75, and you can see it's got those kind of jagged parts to it right there. This is exactly like we were expecting we were going to see. Not a smooth curve, but instead some straight line chunks attached to one another right there. What I'm unhappy about is this is a kind of hard graph for me to read right now. I kind of want to like alter kind of a bunch of the features of this right here. So technically this worked, but we want to alter kind of a whole mess of things about this. So I'm going to go ahead and copy this, but I want to do way better with this. All right. A couple things that I kind of want to do here are this. Let's see here. One thing I want to do, and so notice here that showing is the last thing that we're going to want to do. One thing I want to do is I want to add on like a background grid so I can help myself see some numbers. So one thing I can do is I can do plot.grid. The default for plot.grid is false. I want it to be true. I want to turn on the grid. This says turn on a background grid. You have to use capital T for true. Notice it's green. That means it's a specially recognized word in Python. And when I run this guy now we get the same graph, but it's got a nice background grid on it right there. That's pretty cool. What other things do we want to do right here? Some other things I might want to do is indicate the initial and final points. Those are kind of special to me. Where did we start? Where did we end? So notice that the default in matplotlib is to just draw a line between the points that you're giving it. But if you just straight up give it just one x value and one y value, then it will just do that. It'll just plot a point that's sitting right there. So I'm going to do another plot.plot command. As well as plotting the line, I also want to plot dots. So you can do lots and lots and lots of plot.plot commands, and then one final plot.show, and it'll do all those things on the graph all at once right there. So I'm going to do plot.plot. What I want to do is I want to plot my initial point, the point that's sitting down here at my t0, y0 point. And notice, rather than giving the whole list, I'm just giving it a number and a number. It's just going to plot just that one point. I want to indicate this is where we start. So I want this dot to be green, and I want it to be a dot. So I need to indicate those two things. Matplotlib has a pretty convenient, intensely short shorthand for these things, where after, as a third item in your function input into plot.plot, I can indicate things like G for green, and a period indicating that I want it to be a dot. So that'll say make it a green dot. And we look at it and we see, oh, what do you know? I have a green dot right there. Now, that dot wasn't quite as big as I hoped it was going to be, so I can make it bigger. Let's make the marker size be, I think the default is 5, so I think I'm going to make it like 10. Hey, there we go. The dot's a little bit bigger. If you want a massive dot, make a massive dot down there. I don't think that's very practical for us, but that's okay, right? So you can play around with that too. I want to do essentially this exact same thing right there, so I'm going to copy and paste this, but I want the final point. I want to get our final thing in the t-list as our final ending time, and I want to get the final thing in our y-list, the last element of the y-list, as our final time, our final y value. And since this is the end, I'm going to make this a red dot instead. And oh, nice, we have our starting green dot, we have our ending red dot. This is all coming together real nice here. Now, another thing that I want to do right here, all right, 1 second, please. Another thing that I want to do here is I would like to do two things. One, I want to also add on to this graph the graph of the true solution. And then there's going to be two graphs on here, and therefore I would like a legend so I can tell which one is which. So this is another like good one, an intermediary. So we're going to do one last grouping of code down here, but we're going to need to do some more stuff right here. So let's define the known true solution. All right? So what I want to do is I want to define, and I'm going to call this our actual, will be the name of this function right here. We know that our actual function only takes in t values, right? And I want to pop back over real quick here. Remember that when we came up with our actual solution right here? It's this. I'm trying to graph this function. This is my y of t function right here. So I just want to draw the graph of this guy right here. We're going to need a little bit more help to make this guy happen. One more library to help us do this, because e to the power of is not a math operation e to the power of is not an operation that Python knows. So I need to bring in a math library that's going to help us out with this one right here. All right. So let's pop back over and do that. So NumPy is the numerical Python library. So we're going to import NumPy. Just as with matplotlib.pyplot, we don't want to have to use that phrase every time we ask it to do something for ourselves. For the very, very common thing to do is to call this NP. NP is our shorthand for NumPy, which is our shorthand for numerical Python, which is a massive library of mathematical things. And one of the things that we want out of this is an exponentiation function, e to the power of. So that's one thing we'll use the NumPy library for here. So let's define our function that's going to do this for us here. What we want to get out of this function is when we plug in t, we want to get out, and what was that function that we were looking at here? I'll call this 0.5 times 3e to the 2t minus 1. I'm just going to do 0.5 up front rather than a division by 2 right there. So I'm going to say here, this should be 0.5 times, I wanted this to be 3 times, and now, to get the e to the power of, we have to say, hey, NumPy library, can you do an exponent base e of 2 times e, or 2 times t right there? The default for this, let me do this real quick right here, real quick. In fact, let's be smart for ourselves right here. Let's just run that. And I just want to show you, hey NumPy, what's the exponent of power 1? And it's telling that's e right there, right? So you can see that np.exp of 1 gives us e. So 1 is the power. So we want the power of 2t. So let's bring this back in here. And I think we wanted this, wasn't that a minus 1 up there? So that's 1/2 of 3e to the 2t minus 1. Is that right? 1/2 of 3e to the 2t minus 1. So I think this is going to give us our correct values right here. Notice that we can check it. By checking out what's going on in time 1. And there's exactly that 10.583 that we had come up with over here, right? There's our 10.5834. It just, we did y of 1, actual of 1, and we got out exactly that value right there. All right? All good so far. So to be able to plot this, here's the unfortunate thing. The unfortunate thing is I can't just say NumPy plot this function, or sorry, matplotlib plot this function. What we have learned is that matplotlib plots by doing lists of numbers. So I need to create a list of or t values that are going to go into this thing. And I don't want to use my crappy list of only 5 numbers for my t value, or else I'm going to get a chunky curve just like I got up above. I want to get a whole bunch of input values and a whole bunch of output values according to this. So let's go ahead and generate a finer t list and y list for the actual function. We need to name them something different than t list and y list because I don't want to write over the top of those right there. So I'm going to call this t actual, and we'll call this y actual right here for our 2 lists of t values and y values. So what I want to do is I want to say NumPy, hey listen man, what I want to do is I want to create a list that's a whole bunch of numbers from 0 to 1, our interval of interest, but I want there to be a lot more numbers in there, and I don't want to have to like specify all the ones that I want. So what I'm going to do is I'm going to say, hey NumPy, can you make me a linearly spaced list? Linspace, the linspace function will create a list of linearly spaced values. I want it to start at 0, I want it to end at 1, and how many things do you want in there? How many x values do you want so that this looks like a smooth curve instead of like a bunch of jagged lines? All we need is a number that's big enough that you feel like it looks like a curve. So I don't think we need to go too crazy here. So this will create 200 evenly spaced points between 0 and 1. What I want to do with those t values is plug each of them in to this actual t function right here. So here's the way that I'm going to do that. I want to create a list here, and this is just a manual list construction rather than a function list construction right here. And what I want my y actual to be is outputs, a list of outputs from the actual t function. So I'm going to do exactly that. what should the objects look like in our list? They should look like actual of t. And I want to say that this, I just don't want to overwrite the t that we're using, but I think we're fine with this here. Notice that we're kind of double using variables. That's sort of a bad thing to do right here. Maybe I'll call this AT for like actual t values that we're using right here. It doesn't matter. I'm going to define what AT is in here in a second. I want them to look like the outputs from the actual function where for each AT value in t actual. So this is going to say for every value that's in the t actual list, this linspace list right here, plug each of those individual values into the actual function that we wrote, the function named actual, and those should be all of the outputs associated with our y actual result right here. Right? This should be our list of y values that we're getting. So we've generated two lists right here. So let's see what this looks like. Our t actual list looks like, hey, this is 200 numbers that went from 0 to 1. And it figured out for us how to space them so that they're evenly spaced apart. Notice that if I change this to y actual, this did start us at 1 like we expected it to start us. And where does it end us? Oh, right here at 10.583 like we expected it to end us. So it looks like these are all of our intermediary values that literally truly lie on the solution curve always right there, because these all came from our exact solution curve right there. Right? So I'm going to get rid of this since I don't want that gigantic block of code blocking me up right there. But recognize that you could check that for yourself to see that these are producing that stuff that we want. So now let's bring it all together and make one last awesome graph right here. I'm going to grab all my old graphing stuff and we're going to add on to it. So here's what we're doing. We're going to plot the approximation from Newton's method. We're going to plot the exact using the actual things. So to do this, we're going to do our plot.plot. So we're just going to give it the two lists, t actual and y actual. But I now kind of want to distinguish between the two graphs so that they don't look the exact same right here. And by the way, these are some, that's more of like a graph modifier, so I usually put that a little bit lower down here on the bottom. The ordering of these doesn't necessarily matter. This is just the way that I often organize my things right here. So here's the thing that I'm thinking. I want to plot this as my like actual curve right here. So let's like kind of pick something as to how we want this to look right here. Maybe we want this to be our thing that's actually in blue, and let's make it the regular line like it should be. A blue line right there is how I can indicate that guy. Alternatively up here, let's plot our approximation as maybe like a red dashed line. Two dashes will make it a dashed line instead of a connected curve right there. All right? Let's go ahead and see what this looks like here. Oh, baby. Oh, man, this is cool. So I can see still sort of the jaggedness of my dashed line because it's only 4 parts. I can see where it started and where it ended, and I can see that it's separating. One last thing I want to do is, since there's two different graphs on one graph, I want a legend. So let's add a legend in here. Now, adding the legend should be a graph modifier, so I'm just going to do plot.legend, I think is all I need. Briefly check my notes here. Yeah, oh yeah, that one doesn't need a true for some reason. I don't know why that is. But what we need is we need to know what the legend should look like. So what we're going to do is we're going to come up to our plots and we're going to add labels to each of those plots so it knows what to do. Our approximation, right? Okay, I'm going to do the easy one first, then I'm going to show you something fancy to do for the harder one. This, I want to label this as our exact answer, or I'll call it solution, exact solution. And so I'm just going to run this code right now as it is, and so you can see it brought up exact solution for the blue curve right here. The thing I want to do for this is I want to say this is our Newton's method approximation, but I want to say how many steps we did. I want to say this is our Newton's approximation with n equals 4 as our number of subdivisions. And notice that's a variable that I want to include in like a phrase. So fortunately, there's a handy-dandy way to handle that with a formatted string in Python. So rather than just doing label equals and opening up a string, here I'm going to put an F right in front of those open quotes right there. And I'm going to say this is our Newton's, ooh, all right, I'm not even gonna, here's what I'm gonna do. I'm just going to call it our approximation. Our approximation with n equals, and what I would really like to have right after n equals is 4. And notice that 4 is the value of the variable n right there. So what I'm going to do, because this is a formatted string, is within curly braces, we can actually write code in there. And it will interpret that to be the 4 that it's supposed to be. And then I'll go ahead and close up my string right there with another thing, right? So this is a string because it is enclosed by quotes. I stuck an F in front of it to say, hey, listen, I'm going to include some code in that string that I want you to evaluate as a string, and that's always going to be done with a little piece of braces right there. So now I can go ahead and do this, and oh yeah, dashed line is our approximation with n equals 4. Blue line is our exact solution right here. We can see where our approximation starts and where it ends, and now we can do some nicer things like go all the way back up now to our stuff up here and say, well, let's improve this to 40 and see how close our curve looks. I'm going to run this cell, and I guess all of our ones in between. I don't think I need all of them, but now look, now with our approximation with n equals 40, oh man, we're getting a nice and closer one right there. Notice we could also do other graph modifiers, like a plot dot title, I believe it is, and I could say, oh man, all right, so since there's two different ways to type quotes, notice you can use a double quotes that'll allow you to use a single quote inside without ending the string. So Newton's method approximation. And now we have a title on our graph, stuff like that. So this is pretty cool right here. So we can now literally watch our graphs approach the known graph that we should be getting out by increasing this. And notice here that like, I bypassed what I was looking to modify right here. See, now I'm losing myself in my code here. Why do I still have this giant list? Nice thing you can also do in Jupyter Lab is click on this blue bar and it'll collapse all that into just a little abbreviation right there. And in fact, I don't want to see that anymore, so I'm just going to comment that out so I can get it back easily. I'm not deleting it, but it's never going to run that anymore. Now I can do things like change this to 400, and we're going to see now that this is going to essentially just lay on top of itself. You can barely even see it, that the red curve is just laying on top. But I can really see that the dashed line is like exactly on the blue curve at first, and the red dashed line is starting to depart a little bit from it right there. Notice some other nice things that we can do here are, we can modify other parts to this. What if I really wanted our solution to actually go out to time 4 instead of time 1? Well, let's go ahead and look. Time 4 is now our ending time. Can we just change literally just that one number and just get an updated graph? Yeah, okay, so what was the only thing that we did? Oh, I see what we did right here. I want to make this A and B for our time actual. The way that I know that is our actual solution, our exact solution, only went from 0 to 1 because that was the only stuff I defined for our lin space here. Let's make it go the full span from A to B. And there we go. And so now we can see that we're really, really close for a while. But once this thing gets steeper, it seems like steeper functions are causing our approximation to fall off a little bit more because every time it's a steeper function, our linear estimate of the slope is missing by more and more of the true curvature of the graph that it should have been identifying right there, right? So I hope that you feel highly satisfied with this if your code is running right now. So certainly your mission is to attempt to imitate the code that we've done right here. So I'm going to show our cleaned up version, right? We defined a function using def and a colon. We returned a value, the output from the f of ty function. Remember, this one didn't require any t stuff to compute it, but I left it there so that later when you're doing your homework and you want something like this, it's going to be trivially easy for you to modify your code to make that work. We initialized all of the required variables that we were going to use throughout our code. And notice the one screw up that I had was that I didn't use a variable and a value. I hard coded 0 and 1 there. That was a mistake on my part. I should always be using those variables in there, right? So up here then we did Newton's method. So this is all that Newton's method is literally just that stuff right there. This was us saving information so that we could make graphs. This was just creating variables that would be changing over time rather than a permanently fixed variable like t0 and y0. We checked our stuff with the t-list and the y-list. We didn't need those. That was just to verify that they looked good. We need to use two different libraries here. One, the matplotlib library to do plotting things. We gave the library that has a long and crappy name a nice, easy, abbreviated name so that when we ask it for favors, it's easy instead of annoying. The primary matplotlib functions are the plot function and the show function that we used here. And it always takes in a list of all of the inputs and then the corresponding list of all of the outputs right there, the t-list and the y-list, and that gave us our most simple function. We added some functionality by asking it to turn the grid on with plot.grid parentheses true. We did other things like modifying what type of graph we're seeing right there. This was saying instead of do a graph, do dots and make them green and make them bigger. Here we said grab the last item in the t-list and the last item in the y-list by slicing out the -1 index, count backwards, and then make that a red dot and make that also a little bit bigger to get our endpoints on there. That was maybe less interesting today. Those endpoint dots are going to be really useful for us when we do our two-dimensional stuff next week, which is why I did that. Then we recognized that if we wanted to graph our actual solution, we need to get a list of inputs and outputs for that. Making the list of inputs would have been annoying, so we used NumPy to generate a linearly spaced list of values between A and B, 200 values. That's just the syntax for that function. We also used NumPy to get our e to the power of function right there. That was the two things we used NumPy for. We checked that, that this was giving us our correct final answer. That's just y of 1 right there. We produced a new t-list and a new y-list to correspond with the graph of the true solution as opposed to the graph of the approximation. And then we threw everything together in one nice big graph. We plotted the approximation that we got from Newton's method by using our original t-list and y-list from above. I chose to make this a red dashed line, but that was just a style choice by me. Play around with that if you want. I stuck a label on it. This label was really getting read by me turning on the legend down there. If we just stuck those labels on there and didn't write the line plot.legend, then we still wouldn't have ever got the labels. Those would have been associated to it under the hood, but to see them, we had to turn on the plot.legend. The other thing I did is I indicated the starting and ending ones. Those are the ones that we just talked about. I copied, oh, sorry, I skipped a line right there. This was our approximations. This was our exact stuff. So our t-actual and y-actual lists that we made came into this guy. I made this a blue regular line, and I gave it a label. Indicated our starting and ending of our approximation. Again, kind of lame here, but going to be very useful next week. And then we did some modifiers. I very often like that background grid to help me see some like numerical estimates of some values. When I threw a title on there just so that you can see it, that's a pretty easy thing to do. We turned on the legend so that it would read in our labels. And then our last step always of the plotting is to show the plot that has been created. It's created the plot. It knew all that information. And then we have to say, okay, now show it to me right here. And so we were able to do that. So a bunch of really, really cool stuff that we're able to do here today. Notice that really a big thing here is that Newton's method took up all of what? Like technically like 2 lines of code. Okay, 3 lines of code if we're in a non-autonomous right there. That's all of Newton's method right here. But we wanted the surrounding code to make a robust solver and grapher so that now when you go to do your own problems, if you want to change the differential equation, trivially easy. If you want to change your bounds, trivially easy. If you want to get a better solution by increasing the number of approximations, trivially easy. If you want to see what your t-lists and y-lists look like, which are exactly the types of things that we see over here, notice that we get, we do this, and come on, do the thing, do the dance. Why is it not? Oh, I got to click one. So notice here, it's exactly giving us all of these time values that it's looking at right there. This is exactly this type of stuff that we just computed. Exactly. A t-list, a y-list. Ooh, individual graphs. So this is a system, so there's individual graphs. So next week we're also going to want a second graph rather than just the curve out here, but the individual solutions as well. But it's really just going to be more of the same matplotlib code that you've seen. Also notice one really nice thing here is we're now starting to see that I can see these straight line pieces getting generated right here. That's because they're using delta t being 0.1. And when we make delta t smaller, it increases the accuracy of our approximations. Those are smoother curves there. This is exactly the delta t in our Newton's method code that we've been altering right here. So hopefully you found today, I'm assuming many of you found today to be slightly frustrating, but I am also hoping that you feel highly satisfied in our ability to, in about 1 hour right here, go ahead and produce all of this content on our own, and in fact some slightly better graphs. We're going to see next week that we like our graphs better than the ones that we're seeing, I think, in our slope and direction field things here. So let me leave you with this last bit here. I know this is obviously a long video, but it's a big topic here. So here's the last thing I want to suggest to you is a challenge. The van der Pol equation is something that our book talks about in 2.4. The van der Pol equation is a second order differential equation stated here. Given the initial conditions of x of 0 is 1 and x prime of 0 equals 0, what I would like for us to do is to a 800 step solution to approximate the solution at time t equals 8. So that'll be your final time. Since there is no such thing as a second order Euler's method, we instead need to convert this to a system and do a system approach. So this is actually 2.4's topic, not 1.4's topic right here. So to do this, we need to convert to a system, as we've converted to a system multiple times here by doing dx dt equals v, that's x prime, and then solving for x double prime to get dv dt. You would need to define a function for each of the equations in your differential equation, not just your single differential equation, but now two differential equations. You would need to generate a t-list, an x-list, and a v-list, not just a t-list and a y-list like we did today, but that's just building another list. It's copying and pasting and changing some names. Your graphs will no longer have any t component, right? We went from time as an axis and value being the vertical axis to just having dependent and dependent variables as the two axes, and time being something we sort of have to like interpret along the way. So your new graphs should not be doing t-list, y-list. They should be doing x-list, v-list right there. And this is something that you should attempt to do on your own before you watch the next video next week. At least attempt this. You should see that this is not that terribly difficult. If you have your code working for today, then you kind of just need to do a bunch of copying and pasting and changing some values to get the new thing that you're going to want for the next week out here. All right? I think you can do this, and you should definitely try. All right? The last thing I'm going to say to you is this. I am strongly assuming that several to many of you, perhaps a majority of you, are going to end up getting stuck, and your code is not going to work, and you don't have this picture right now despite attempting to follow along with me. You should go back through the video and see the parts where I wrote the code that seems to be giving you issues and see if you can fix it yourself. You should Google things. You should Google things like the exact quotes that you're seeing in the error message that are popping up to see if you can figure it out yourself. And what you should do is, if you're stuck, is you should contact me and have me help you. Email me and say, I'm not getting this to work, those lines of code work, these ones don't, I don't know what I'm doing wrong, here's what my code looks like. Come to office hours and have me help you. I am specifically not going to post this code as a document because I want you to try on your own, and I want you to talk to me if you're stuck, rather than just trying to get through this by copying and pasting. So I could easily post this code for you, and I'm not going to, because I want you to contact me if you get stuck so that I can help you with this stuff. That's really meaningful, that we have a legitimate coding experience and not a copying and pasting coding experience here. All right, so try, get stuck a little bit if you're stuck, but don't just get stuck forever. Have me help you. That's the point of all this stuff. That's why I have 6 hours of office hours on Monday, Tuesday, and Wednesday. That's why I answer my email occasionally and will be looking very much for your emails, because I expect people to get stuck here. That is normal. Get help if you get stuck. And I look forward oh so much to doing a bunch of even way cooler stuff with this next week. And for next week's videos, we're going to build very much off of this idea. I might even go so far as to say I'm going to copy and paste all this stuff into a new document, and we're just going to build more lines of it to make our systems happen. But we're going to add some extra functionality to our things later. So this is sort of our, like, can we get some basic graphs like this generated right here, so that next week we can do some more complicated things to build off of these. So I'm very excited that we're here doing our little bit of Python programming. We've got systems coming up. We've got runga kutta method coming up. And I'm also going to show you another little like bonus thing, which is an iterative method, just like Newton's method is an iterative method, but an iterative method for actually determining analytic solutions rather than approximate numerical solutions to differential equations, which is a pretty cool thing that I think kind of goes with this, because we're seeing that this is a method where it's like repeat a process literally 400,000 times. That's literally what we're doing right here with our for loops. And so I want to show you that there is an iterative exact technique that goes along with like actually using variables rather than numerical calculations. And we'll hit that at the end of our little unit on programming here as well. So get stuck, struggle like every programmer on earth struggles, go to Google, and then go to me. And let's make this happen here. You should have this graph being very nicely produced for you by the end of this. And I'll have some homework questions that are going to ask you just for some numerical approximations, ask you some questions about some graphs here. So your homework will be dependent on you having some running code here. So it matters that you hit me up and contact me if you get stuck with any of this stuff right here. Good luck. Contact me. I look forward to helping all of you guys. I will see you guys with with systems and I guess second order differential equations in Python next week. Have a good one.